For the next couple of modules, we want to step back a little and think about how climate has changed in the past, and hopefully that's going to help us understand some of the constraints and possibilities that affect potential climate change today. But first, how would we even know what past climates were like? Well, by about 150 years ago, there were enough temperature measurements being taken regularly that we feel relatively confident putting together a direct temperature record. Now, we can't say exactly what the average surface temperature on Earth is because we don't have temperature readings from every spot on the surface, so we have to do some estimation. But today, there are several major efforts to report the global surface temperature. They all differ slightly in how they account for missing data, precisely what data set they use, quality control procedures, things like that. Thus, at the fine scale, they provide slightly different answers to questions like whether 2016 or 2019 was the hottest year ever on record. But at the larger scale, they all tell an extremely consistent story of warming over time. Now, if we want to know about times before we had a sufficient and consistent set of surface temperature measurements, we have to look at climate proxies to estimate what the temperature was. Proxies are a record other than direct temperature measurements that you can use to estimate what the temperature was. There are two things you need in a climate proxy: a way to say something about climate conditions like temperature and rainfall, and a way to determine the time period that you're looking at. For this reason, tree rings can be a really good climate proxy. Most of us learned when we were kids that you can tell how old a tree was, at least in temperate climates, by counting the annual growth rings. So, if we cut down a 300-year-old tree today, we can look back and see how well it grew in any particular year over the last 300 years. Good years will have wide rings where the tree grew rapidly, and poor years will have skinny rings where growth was slow. Most trees grow well in years when there's sufficient moisture and warmth, so if you know a little about the requirements of a particular tree species, you can often say something about its growing conditions by looking at its rings. To talk about local climate, you need to average the growth of multiple individuals so that you don't, for example, misattribute a few good years to climate when really what happened was that a big tree fell down and opened up more light for your subject tree. But this is usually pretty straightforward. Moreover, if you look at multiple species in a region, you can compare varying growth rates and separate out variables like temperature and moisture. Many regions of the planet have trees that are at least a few hundred years old, but tree rings wouldn't be nearly as valuable as they are if we could only look at recently living trees. But people have been building with trees for a very long time, and if we combine a rough knowledge of the time when a building was constructed with a fingerprint pattern of good and bad years, we can use overlapping records to go back in time, sometimes over 1,000 years. In fact, some trees preserved in bogs provide ring data from up to 5,000 years ago. This just gives a hint at the uses of tree rings, but hopefully you can start to see how they'd be part of a global record of temperature estimates going back well beyond direct temperature measures. Another great temperature proxy can be foraminifera and diatoms in ocean sediments. Foraminifera and diatoms is a mouthful, so we'll just refer to them all as forams. Forams are little single-celled marine organisms that produce a carbonate or silicate shell that differs by species. Marine sediment can be dated using radiocarbon techniques, and it builds up on top of itself over time, so if you drill out a sediment core, you know that things are in one particular layer were deposited at about the same time as other things in that layer. Different species of forams have different ideal temperature ranges, so scientists can remove a core of marine sediment, determine dates at different depths, and then have their grad students sift through the sediment looking for, classifying, and counting all the microscopic foram shells in a layer. And you can use this to determine water conditions at the time. Even more commonly, scientists measure relative levels of various isotopes in their shell to estimate water temperatures. Marine sediments can go back much farther than tree rings. It's amazing the different things that scientists have used as climate proxies in order to build up a complex and global understanding of past climates. Pretty much anything you can think of that builds up over time in discrete layers has probably been used by someone at some time as a climate proxy. For example, speleothems, the fancy word for stalactites and stalagmites, which younger you thought were impressive words enough, but not enough for scientists. Anyway, they grow over long periods of time and are good proxies because they retain various isotopes that can be used in temperature estimation. And the same is true for things like corals and reefs. Lake sediments can record erosion from nearby mountains. Pollen grains can be used like forams in terrestrial deposits. Wind-blown glacial dust builds up in useful ways in a few places on Earth, and so on and so forth. In one of my favorite temperature proxy studies, scientists discovered a cave that had harbored rats on and off for over 100,000 years, and like anyone would, they saw the rat feces that had built up over all that time and thought, Eureka, a climate proxy! You can even drill a borehole into the crust, just a big hole in the crust, and directly measure the current temperature of the rock, and you can use that to determine surface temperatures for the last several hundred years. That one kind of blows me away. At this point in the mini lecture, Katie's getting very frustrated with me, wondering why I'm talking about rat feces but ignoring one of the best proxies we have, ice cores. Well, I thought I'd save that for last. There are numerous places around the planet where snow never really melts, but instead it builds up over time and forms glaciers or ice sheets. In these places, new snow falls on top of the old snow, and the pressure of snow on top slowly packs down the snow below. Under pressure, the lower layers of snow turn into ice and slowly trap gases in little bubbles in the ice. It can take up to 50 years for gas in the ice to be fully isolated from the atmosphere in that way, so ice cores give you an average of many years of data, but if you're looking at a 500,000 year record, a 50-year moving average is pretty great. You can, for example, measure the concentration of carbon dioxide in these bubbles to be able to tell what the atmospheric concentration was at the time. In addition to trapping gases, ice cores are wonderful where you have them for several reasons. First, there are clear annual layers. On many glaciers, snow builds up over the wintertime, and then some of that snow melts in the summer, creating different textures to the snow layers, just like growth rings on a tree. Even in places where the snow may never melt, like East Antarctic ice sheet, the sun shines only in the summer, and that creates sublimation, which leaves a clear annual record. So you can quite precisely date your annual layers as long as you have a grad student around who wanted to stay out of foram work. Even better, you can examine the water in the ice to determine the isotopic ratios and use that to say a lot about temperatures. We mentioned isotopes before, so I guess it's time to explain them for those who've forgotten their chemistry. The chemical properties of an element are determined by its atomic number, which is the number of protons in the nucleus. All atoms with the same atomic number will bind in the same way, and so on. The mass of an atom, however, is a function of both the number of protons and neutrons. Atoms of the same element, but with different numbers of neutrons in their nucleus, are called isotopes. Chemically, they act identically, but they'll often have different radiological properties, and they'll also have different masses. You may have heard the term heavy water, which refers to water where there's at least one hydrogen atom with a proton and a neutron in the nucleus, rather than the usual boring hydrogen with just a proton. This hydrogen atom is twice as heavy as a typical hydrogen atom, and its atomic mass is about 2 rather than 1. Heavy hydrogen is so important that it has its own name, deuterium. There are even hydrogen atoms with 2 neutrons in addition to the proton, and we call these tritium. Pretty much all the elements have a few isotopes, but they don't usually get typical special names. We just call them things like carbon-12 and carbon-13. Now, why do masses matter if the atomic properties are the same? Well, imagine I had a box filled with wiffle balls and baseballs, and I started to shake the box up. Which balls would be most likely to bounce out? Well, the wiffle balls, of course, because they're lighter. That's especially true if I'm only shaking it up a little bit. If I start shaking it up much harder, then more of the wiffle balls will bounce out, but so will some of the baseballs, and the fraction of baseballs in the final count of all balls on the floor will increase. It's the same with water molecules. Think about gas that evaporates from the ocean. At moderate temperatures, that's going to be mostly water containing only the lightest isotopes of oxygen and hydrogen, because those water molecules are the lightest, and so it's the most likely to be bounced hard enough to catapult out of the liquid into the gas. So, when ocean temperatures are low, the atmosphere gets relatively enriched in light isotopes, and the heavy isotopes stick around in the ocean. As that air that evaporated away moves away from the ocean and over land, the heavier isotopes will rain out of the snow first, and the snow that falls inland over glaciers and ice sheets will be strongly enriched in the light isotopes. On the other hand, when the ocean or atmospheric temperatures are high, then lots more water evaporates, and that water is going to have much higher mix of whatever isotopes there were in the water, so there are a lot more heavy isotopes in that mix. Thus, when I look at the isotopes in my ice cores, heavy water suggests that temperatures were high where the water evaporated and vice versa. There's a lot more you can learn from various isotopes as well as from ice cores, but hopefully this gives you a glimpse of why they're so valuable. Of course, one of the tragedies of climate change is that so much potential information about Earth's history is being lost as mountain glaciers retreat or disappear entirely under the changed conditions. If you want to go back even farther than you can with ice cores, your options become much more limited and less precise. Global sea levels can give you a sense of how much ice the planet held, so that kind of information can be helpful. Some sorts of minerals require fairly specific conditions to form, so those can help you in a big picture sort of way. You can glean information about carbon dioxide by looking at plant fossils and counting stomates and so on and so forth. With all these different methods at our disposal, we can construct a fairly accurate record of global temperatures for the last few thousand years, with regional records from the major ice sheets in Antarctica and Greenland going back several hundred thousand, and a general picture going back even farther. In the next mini lecture, we'll talk more about what these records show.